Hello and welcome again to my physics video lecture supplement series. In today's video, I want to work through an example of a wheel which is rolling down a hill, and this wheel is rolling without slipping. The example is drawn here on the board beside me, and I've written out the basic parameters that have to do with the wheel here. Essentially, the wheel starts at the top of the hill. It starts rolling without slipping down the hill. It reaches the bottom of the hill. In doing so, it changes height from 2 meters to 0 meters above the base of the hill. The wheel itself has a 10 kilogram mass, and it can be treated as an annular disc or annular cylinder whose inner radius is 25 centimeters and whose outer radius is 40 centimeters. What that means basically is that we're modeling the wheel as being starting with a solid cylinder of radius 40 centimeters, and then we're drilling a hole through this cylinder where the hole's radius is 25 centimeters, and it's through the middle of this cylinder. And so what we want to know is when it reaches the bottom of the hill, what is its translational speed, what is its rotational speed, what is its translational kinetic energy, and what is its rotational kinetic energy. Now there's two basic concepts which are going to be applied in this example. The first one is conservation of energy. And the conservation of energy says that the final energy and the initial energy need to be equal to each other. The second concept that we're going to apply is rolling without slipping. So what rolling without slipping says is that we can relate the translational speed, or the center of mass speed, to the rotational speed by noting that the outer radius of this wheel times the rotational speed is equal to the translational speed. Or similarly, that the rotational speed is the translational speed divided by the radius of the wheel, the outer radius. So we're going to end up using both of these to solve the problem, but let's start with our conservation of energy. So we need to look at what energy does this thing have initially and what energy does it have finally. Initially, it's at rest at the top of the hill. So all the energy is potential energy. So the initial energy is mg h initial. And the final energy is the energy it has when it reaches the bottom of the hill. This is going to be whatever potential energy it has at the base of the hill, mgh final, plus kinetic energy from translation, plus kinetic energy from rotation. So conservation of energy says we should set this one and this one equal to each other. And let's go ahead and take the base of the hill to be ground. So in other words, the initial height is 2 meters because it starts off 2 meters above the base of the hill. Another way of saying that is that we can ignore this term here, get rid of the potential energy from the final, and just subtract it from the initial. So our initial potential energy is really mg delta h. And for what it's worth, this initial potential energy comes out to 10 kilograms times 9.8 meters per second squared times 2 meters, and that comes to 196 joules. So I'm going to put that up there right now to use as a reminder for later, because we're going to be finding some kinetic energies at the end, and hopefully they add up to 196 joules. So the rest of conservation of energy says we need to set this thing and this thing equal to each other. So mg delta h is 1/2 mv final squared plus 1/2 times I omega final squared. And you may be wondering why I put so much space between the moment of inertia and the rotational speed. The answer is because I have an equation here which relates the rotational inertia for an annular disk, in other words for our wheel, to the mass and the 2 radii. So we might as well just substitute that in right now. So mass divided by 2 times sum of the 2 radii squared. Okay, so that gets us conservation of energy, and we have one equation here that has 2 unknowns in it at this point. The speed, that is the translational speed, and the rotational speed at the bottom. So at this point, we need to use our rolling without slipping equation, and we need to make a substitution of R naught of the outer radius times the angular speed in exchange for the translational speed. So that gives us mg delta h is equal to 1/2 m R naught squared omega f squared plus, let's go ahead and combine some terms. So we have 1/4 times m times R naught squared omega f squared plus another 1/4 times mass times the inner radius squared times the angular speed squared. So here is a good time to start combining like terms. For one thing, notice that there's a mass in all of these terms, so we can sort of divide everything by mass. For another thing, it's worth noticing that there's a 1/2 here, a 1/4 here, and a 1/4 here. So I'm going to go ahead and just multiply everything by 4. So my next line down basically reads 4g delta h equals 2 R naught squared, outer radius squared times angular speed squared plus 1 outer radius squared omega f squared plus 1 inner radius squared omega f squared. So we're trying to solve for the angular speed. So all of these terms have an angular speed in them. So let's, for one, combine our like terms, and for another, let's anti-distribute the angular speed. So what that ends up looking like is 3 times outer radius squared plus inner radius squared times angular speed squared. So to solve for the angular speed squared, we got to divide both sides by this term. So the angular speed squared is going to be 4g delta h over 3 times the outer radius squared plus the inner radius squared. So take a square root of both sides, and we get an answer for the angular frequency. So the angular frequency ends up being 12. So we now have an answer over here. Omega F is approximately 12 radians per second. And so now we want to find the final translational speed. That final translational speed is going to be R naught times the rotational speed. And so that's 40 centimeters or 0.4 meters times 12. So the final speed is 4.81 meters per second. So now we've got those two final speeds. We can go ahead and erase this because now we've got to calculate our final energies, rotational and translational. So the rotational energy is this term right here. So E rotational kinetic is 1/2 times half of the mass times outer radius squared plus inner radius squared times the frequency squared. So actually the frequency squared, for what it's worth, this number squared comes out to 144, and actually there's some round off going on here. It's actually 144.5. And so this guy right here is 0.4 meters. This guy right here is 0.25 meters squared. This guy right here is 10 kilograms. I'm just pulling those from my list off to the side. So plug in all those numbers, and what you end up getting is that the final rotational kinetic energy is 80.4 joules. Okay. Last but not least, the final translational kinetic energy. So that's going to be 1/2 times 10 kilograms times our final speed, 4.81 meters per second squared. So plug those guys in and you get a final translational kinetic energy, ET final, of 115.6 joules. And actually we need it to be in 3 significant figures, but I'm writing it to 4 because I wanted to highlight that 115.6 plus 80.4 is 196. So why is that significant? Because that was what our initial energy is. So our initial total energy and our final total energy are equal. So really this answer right here, if we are doing significant figures, looks like this. And so there's a little bit of round off error in adding the two if you keep track of significant figures, but we've conserved energy, so it looks like we have solved this problem correctly. That's our double check to make sure that everything has been done right. So that's all for today, and thanks for watching. Hope that you enjoyed this video, and I'll see you next time.